Today we're going to talk about Chapter 6, using the standard deviation as a ruler and the normal model. This is something that we'll use all throughout the rest of the year, and it's really an important topic. So have your Chapter 6 notes out and ready to go. So we use the mean and the standard deviation to describe a model only when the distribution is symmetric. Whoops, let me get a pen here. Symmetric and unimodal. And we call this shape normal. Should be an O. In order to use the normal model to compare distributions, we have to check this condition. It's called checking the nearly normal condition. It's really, really important. And as we go through the year, you'll see that conditions are something that we do often, or checking the conditions. So the shape has to be roughly symmetrical. In order to check the shape, we have to make a picture. Well, that histogram can be one of two things. The picture can be one of two things. It can be a histogram, or we can even make a stem plot. We will learn how to make pictures quickly as we move through the year. For now, we're doing them by hand, but there are ways to quickly make a picture and see what's happening. Now, if the mean and the median, or if the shape is normal, then the mean and the median should be equal, and that's really important. Remember that if the data is skewed, then the mean is going to be pulled towards the skew, so towards that tail. And if there is no tail, meaning it's symmetric, then the mean and the median would both be in the middle and they should be equal. So now we're talking about the difference in our terminology. So far, we've been looking at distributions. So these distributions come from real data, things that we observe, like our M&M data or something about our classroom data. And because it comes from a sample, stuff that we collect, these are statistics, so sample statistics. And we use the letters X bar and S. So these guys are based on our sample data. Well, now we're going to switch to, and we're going to go to a model. So that model, these guys are theoretical or ideal data based on the population. So this is based on the entire population, whatever we decide that that's going to be. Well, because it's based on the population, that means that it's going to have a normal curve, and we call it a parameter. So population parameter, and then we have sample statistics. So anytime we talk about a statistic, it comes from a sample versus a parameter is based on the population. And because we're talking about this ideal distribution and this imagined theoretical data, then we have different symbols for that. So the mean and the standard deviation, now our mean, this is mu, and this other kind of circle-looking thing is sigma. And this sigma is our standard deviation. So the standard deviation is a measure of spread and how spread out things are from the center. So we have these two curves right here. This one is smaller. It's less spread out, so we say it has a smaller standard deviation, versus this one, the one that's wider, has a larger standard deviation. So we like to compare these guys to each other. So a standard deviation is a measure of spread or variability. And with a smaller standard deviation, then less variability is present. And if it's larger, then we have more variability. So looking at these two curves, again, this one, they're closer together, so there's less variability. And this one over here, there's more spread out, so there's more variation in what's happening with that data. Now we can also use the standard deviation for measuring how an individual compares to a group. In other words, where do I fall? So if I'm looking at this smaller standard deviation, where am I along the scale at the bottom? Do I fit in the middle with the larger group? Am I up in this tail up here? Am I farther down? And we can use that as long as we get everything into the same units. Now, to measure how far above or below the mean any given data value is, then we have to find its standardized value. And that standardized value, we also call it a z-score. Z-scores are really, really important and something that we're going to use quite a bit. In fact, we started working on them today when we were using the justice tenure worksheet. So we started moving things around, shifting and rescaling. Well, we can shift and rescale any data to make the mean 0 and the standard deviation 1. And this is standardizing those values. So the normal model then has its center at 0 with a standard deviation of 1. So this becomes 0 right here, and then we go out by 1 each time. And it's really useful for comparing apples and oranges. We can take any work from anywhere, any data set, and make them all be comparable. Okay, so here is how we standardize a value. And we look at the z-score calculation. We take an x value, we subtract the mean, the new one, the parameter, and divide it by the standard deviation. So to standardize a value, you're going to subtract the mean, and that's mu. Whoops, that looks bad. Let's erase that one and rewrite it. And we divide by the standard deviation. And that's sigma. To standardize values, because they have no units, they are useful when you're comparing values that are measured on different scales with different units. Again, we're talking about comparing apples and oranges. This is really, really helpful. Okay, so here's our first example. It says, what is your height in inches? Well, I am 5'7", so my height is 67 inches. And I want to be able to standardize my height based on the information I'm given. So this 67, that represents the x in our equation. So it says, calculate the standardized value for your height, given that the average height for women is 64.5 inches with a standard deviation of 2.5 inches, and for men it's 69 inches with a standard deviation of 2.5. So if we're going to standardize that value, we would take the x value, subtract the mean, and divide by the standard deviation. So my x, that's 67, and since I'm female, then my mean is 64.5, and I would divide by 2.5. Okay. For me, my height, this value, my z-score is 1. So what is that, or how do I interpret that? I say that my height is one standard deviation above the mean. Now, the average woman's shoe size is 8.25 with a standard deviation of 1.15, and the average, average male shoe size is 10 with a standard deviation of 1.5. So suppose Sharon wears a shoe size 9 and Andrew wears a 9. Does Sharon have big feet? Does Andrew have small feet? I don't know. So we want to find out who is more unusual. So if we standardize both of them, we get to compare. So we can say, does Sharon have big feet? Does Andrew have small feet? And we can do it this way. So let's look at Sharon first. So Sharon, her x value is 9. So we'd say it's 9 minus, and then we go find this part here. So our average is 8.25 with standard deviation of 1.15. So we subtract the 8.25 and divide by 1.5, and we get a z-score of 0.65. So that means she's 0.65 standard deviations above the mean. Now Andrew over here, he wears a shoe size 9, And he's definitely less than the average. So he's going to end up on the other side. So 9 minus 10 divided by 1 point, oops, that's 1.15 over here. And this is 1.5. And his ends up being negative 0.67. So that means that he is 0.67 standard deviations below the mean. And Sharon over here is above the mean. Now these guys are pretty close, but I would say Andrew is more unusual because he is farther away from the center. So in order to compare values that are measured using different scales, you must first standardize those values. Standardize the values. The standardized values have no units and are called z-scores. Z-scores represent how far a value is above the mean, if it's positive, or below the mean, if negative. For example, a z equals 1 means the value is 1 standard deviation above the mean. And a z of negative 0.5 means the value is half a standard deviations, or 0.5 standard deviations below the mean. So the larger the z-score, and I can say the absolute value, the more unusual it is. So we can use it to compare things. In this example, we want to see how we can use z-scores to compare different two different things. So we have Anna and we have Megan, and they both took a test in French and a test in Spanish. Well, Anna, she scored 83 on both, and her roommate Megan scored a 77 in French and a 95 in Spanish. So who performed better overall? Well, we would want to have two distributions. So this one over here on the left, we'll call this one French. Call this one French. And we'll make this one on the right Spanish. And we'll start placing these. Now, how do we build the bottom scale here? So how do we compare what it goes on the bottom? Well, here we know that we can make standardized scores and have this center be 0 and then have 1, 2, 3. But we can also use the information that's given. So French has a mean of 81 and a standard deviation of 5. So here the mean is 81 and the standard deviation is 5 units. So this space right here is 5 units. So I go plus 5 and this is going to be 86. And then I add 5 more, I get 91, and I add 5 more and I get 96. That's 3 standard deviations. Well, this direction is also 5 units, but it's in the negative direction. So I would subtract 5. This is going to be 76, 71, and then 66. So let's go ahead and place them. Well, Anna, she scored 83. So we'll put Anna where 83 would be. It'd be right about here. This is Anna scoring on her French test. And Megan, I'll put her in black, Megan got a 77 in French, so she's way down here. So this is Megan. Well, who did better in French? Well, of course, Anna did better in French. So Anna, her z-score would be 83 minus 81 divided by 5. And her z-score ends up being 0.4. And Megan, her z-score is going to be 77 minus 81 and divide by 5. And her z-score is going to be negative because she's below the mean. So it's negative 0.8. Now let's go over to Spanish. Anna, she got an 83. Well, I don't know where to put it on the scale, so I need to develop the scale. So I go look at my information. Spanish had a mean of 74 and a standard deviation of 15. So let's go place this in. So 74 goes in the middle, And then this space here, that was 15 units. So if I add 15, I get 89. And I keep building onto that, 104 and 119. Then going the other way, I would subtract. So this is going to be 59 and 44 and 29. Now let's go ahead and place Anna. So Anna got an 83. She's somewhere in here. This is Anna. Still on the positive side of things. And Megan, she did a really good job on this one, and she had a 95 in Spanish, so she's up here somewhere. So this is Megan. Well, looking at Spanish, Megan absolutely did way better, but then she didn't do as well in French. So who did better overall? Well, let's go find the Z-score. So Anna, her Z-score is going to be 83 minus 74 divided by 15, and her Z-score is 0.6. And Megan, her Z-score is going to be 95 minus 74 divided by 15, and hers is 1.4. So depending on how you interpret that, you can say Anna did better overall because she was on the above average each time. And then Megan, she did better in Spanish. So you have to decide how you want to interpret that. Okay, the normal model is unimodal and symmetric. So therefore, it follows the empirical rule. The empirical rule is also known as the 68, 95, 99.7% rule. That was really bad writing. Anyway, what it tells us is that about 68% of all the data values fall within one standard deviation of the mean. Now, in the center, that's 0, so we'll count out 1, 2, 3 standard deviations, and -1, -2, -3. So on this drawing here, we already have the curve and we have where the standard deviation values are. But let's say you have a curve and you have no idea what the bottom scale is. So what could you look for? Well, we look for something called an inflection point. So an inflection point is where it goes from being like mountain-shaped to bowl-shaped. And for us, on this drawing up here, it's going to be right about there. So where it goes from being mountain-shaped to bowl-shaped. We also think of inflection points when you do cubics and graphs, like x to the third. So we would draw that down. Now it matches right up for us, so we're going to draw that down. And what we do know is that in this middle area, that's about 68% of all my data. 68% of all my data. And then if I go within 2 standard deviations of the mean, that's going to be 95% of all my data. Now we can use this to estimate certain things. So this is out 2 standard deviations, and we know that those standard deviations are all the same, and that's going to be 95% of all my data. And then if I go out 3 standard deviations, I get 99.7% of all my data. So that's like almost everything if I look at it. So from here all the way out to there, that's 99.7% of my data. Now, the directions here say describe this model. And you have a couple of homework questions that ask you to do that. So for us in this model, what we're looking for is how to describe the distribution for male heights. Well, our male heights had a mean of 69 and a standard deviation of 2.5. All right, so remember, this is our mu, and this was our sigma for our male heights. N stands for normal. Okay, let's go ahead and place our values in there. So if I were to put my values in here, this would be 69, and then I would add 2.5 to get up there. So this is 71.5, and this would be 74, and this would be 76.5. And then going back the other way, I subtract. So it's going to be 66.5, 64, and then 61.5 way down here. Now, to describe the model, we say between 66.5 inches and 71.5 inches is 68% of all male heights. Another way maybe is to say 95% of all male heights fall between, and we look over here at 2, and that's going to be 64 inches and 74 inches. Now, to finish this off, you need to go back and you need to do 99.7%. So 99.7% of all, and you can continue on with your statement to finish that off. I'm running out of room. Okay, we have more with this in just a minute. Okay, now right below that picture we have another one, and we have this other curve. So I want to fill this out so that we can answer these questions using the empirical rule. So using the empirical rule, we've got the male's heights at 69 in the middle, and then we go up. So 71.5, 74, and then 76.5. I know there's a fourth one out here, but we won't worry about that. We'll just go with 3. And this is 66.5, 64, and 61.5. Now, it says up above in question number 1, we'll do this in red, it says, in what interval would you expect the central 68% of all male heights to be found? Well, the central 68%, you know that that's within 1 standard deviation of the mean. So the central 68% of all male heights, and of course we want to put all of our answers in context, would be found from 66.5 inches, 0.5 inches to 71.5 inches would answer that question. Make sure that you say the whole thing. So the central 68% of all male heights are from 66.5 inches to 71.5 inches, and don't just answer numerically, because all of these need a context answer. Now question number 2 says about what percent of men should be taller than 74. Well, that's right here. So we want this information underneath this tail here, and that is not one of our intervals. But let's take a look at this. This is 2 standard deviations out, and this is 2 standard deviations out. So that's 95% of all my data lies in there, right? So from here to here, that's to 95%. Well, if that's 95% in the middle, then there's 5% left over. So that would be 2.5% down here, and that would be 2.5% up here as well. So about what percent of men should be taller than 74 inches? Well, 2.5%. 2.5% should be taller than 74 inches. All right, now the last one. It says about what percent of men should be within 64 inches to 71.5. All right, so that's here to here. And that's not one of our intervals either. However, if I look at it, then I know that from here to this line, that's going to be 68%. So this half, that would be 34%. And if I look from the blue lines together, that's going to be 95%. So this half on this side, that's got to be half of 95%. So I take my 95 and divide it by 2, and I'm going to get 47.5. Remember, that's this interval right there. And this side, of course, was half of 68%, which gives me 34. So to answer question number 3, I know that it's 34% plus my 47.5% to give me a total answer of 81.5%. And we want to answer that in context. So about 81.5% of men should be within 64 inches to 71.5 inches tall. So more to come on this, but we will be practicing the empirical rule as well as what happens when it doesn't land in these percentages.